Hello, my name is Jeeves, and today's video is about reservoir sampling. This is a very popular interview question, and it's an interview question that I received in an actual interview from an actual company, and I absolutely bombed that interview. Uh, but I enjoy sticking with problems longer, and the purpose of this video is so that you can ace your interviews, and hopefully you can understand the solution as well behind this classic problem that was invented in the 80s and has come up in 2020 to keep you from the job that you're interviewing for. So, without further ado, let's get into it. The problem statement is that given a stream of size n, which is too large to fit into memory, how do you randomly select k elements such that each element has an equal probability of being chosen? All right, so the outline for this video is that I will give you the context and also a mini rant about why I don't think that this is a fair interviewing question and why, if you're an interviewer in a company, I don't think that you should ask this question. Um, but the second thing that I'm going to try to do is going to try to give you a beginner's mind, which is how would you solve this problem if you didn't already know the answer? If you were just guessing, how far could you get? And I would know intuitively because I didn't know the answer and I tried to come up with the best solution that I could, which wasn't correct. And then you can finally see the answers. And then after that, I will build a little bit of intuition about why this is the case. And then we can do some rigorous mathematical proofs because why not? Hopefully it'll be satisfying and it'll tell you why this algorithm exists and why it is correct. So next time, if your interviewer asks you, how would you prove that this is the case? You could say, well, good sir, here is a proof by induction that I bestow upon thee. All right, so I'm going to give you a timeline over here about timestamps so you can skip to whatever section that you want. But let's begin. So let's start with a mini rant. Why is this a horrific question to ask in an interview? Well, there's really only one answer that you'll encounter in the wild. There are actually many, but the other answers are really in the scope of algorithmic research. I don't think that anyone is actually doing this, and if you are, let me know. It is inherently a probability and statistics question and nothing else. So uh, it's about, can you do math? And do you understand the math? Or even if you don't understand the math, can you regurgitate said math? It's unlikely that someone will come up with the correct solution on the fly. People thought about this for a decent amount before they actually came up with it. Um, there are no edge cases. So you're not really testing a programmer's ability to sort of go through the details and see if they can think about all the ways in which you would break. It is an obscure set of randomized algorithms, which is not exactly part of the computer scientist algorithmic foundations course, nor is it something that's going to show up in your machine learning course. They got better fish to fry, and you are exclusively screening for the people who know the answer to this question through schooling or detailed preparers who go through all of LeetCode. So that is why I don't think that you should ask this question in an interview. Also, I think that the better questions to ask are the ones that have multiple tiers of solutions so that you can sort of see, does the person think about this correctly? Can they come up with improvements? Um, this kind of thing. Nothing's perfect, but I think this question is far from perfect and there are better options. So why don't we talk about what this is useful for? When will you ever have n items that are too large to fit into memory and that you need to randomly, unbiasedly sample k elements? Well, turns out, uh, you know, maybe you're searching through queries like Google queries, and you're trying to randomly sample k elements such that you get an idea of what the traffic was for that month. But the kind of weird thing is that also has to be pretty large because you don't want your sample to be biased. So k needs to be large enough so that you feel like it's a sufficient sample of the real data set. But why wouldn't you just be happy with the first 1K or the next 1K? Maybe because that's biased towards recency. But again, who cares? I don't know. Uh, I think that this code shows up in uh, database streaming applications potentially. But if you utilize this algorithm in production, please email me and educate me on when this will show up in my real life. Uh, and I'd love to learn. So, or drop a comment below and on YouTube, and we can all learn from each other. All right, that my mini rant and context is over. Okay, so let's go back to the problem. All right, which is you have a stream of size n, and you need to randomly select k elements. All right, so the first thing that you probably think is that it seems like we can't use O of n space, so we need to do a lot better than that. So we could use perhaps O of k space, and maybe we could use a list or heap to keep the k elements. And heaps are good at finding the max k or min k if you've done problems in which you have a stream of numbers and you're trying to find the top k elements. You know, this should seem very similar to that. But then the problem is, what does it mean to be random? What does it mean that every element has an equal probability of being chosen? Well, I could fill in my array with k elements. And when I get a new element, I could pick a random index to replace. That's pretty random, right? But then with what probability do I replace it? I don't know. Can I just flip a coin? Does it matter? Is 50% fair? You know? So this is the heart of the question, which is I fill an array with k elements. We'll call this the reservoir. And how do I know which element to replace? And with which probability do I replace it? And so, you know, um, if you can't figure this out, then you are screwed. Um, and so that is the problem. And so to answer this question and to think a little bit more slowly, it's like if you were to flip a coin and every time that coin lands heads, you were to pick a random index and replace it, that wouldn't be fair. Each element wouldn't really have an equal probability of being chosen because for the first element that you put into the reservoir to survive, it needs to win n coin tosses. In other words, n has to come up tails, for example, um, if you're doing this consistently, for that element to be in the reservoir versus the last element has a 50-50 shot of being included in the reservoir. So flipping a coin is incorrect. And picking any random index, while it has the right idea, is not quite what you're searching for. And so that's what I mean by if you started with this approach, you get stuck really quickly right around here. All right. So why don't we look at two answers? Okay. And so we're now moving on to the algorithmic approaches. This is the code for reservoir sampling. This is what I've written up. It's not from Wikipedia or anything. This is my Python implementation. So feel free to steal it. But you iterate over the entire stream. You populate the value. And now what you do for I, which is greater than k, is that you select a random integer between 0 to I, where I is ever increasing as you go through the stream. And if that index is less than k, then you take that index and replace it with a value. And so each element that is being added to the reservoir is added with probability k over I. Why is this the case? Why is this correct? Well, if you're asking that question, then stick around for the latter half of the video. But suppose that you didn't do that. Kind of another interesting solution, I think, is this one-liner, which I'm oddly proud of, is that you could just take the stream, you could assign a random number to every element, and then you could return the top k elements, which would have been selected by random. All right, so you could still, if you're an old dog who can't learn new tricks, you could still do that, and you would have roughly n plus n log k runtime, because the construction of the heap or inserting an element takes log k time, and you would have done this n number of times. And if this is sufficiently small, then all right, you got a linear algorithm. Is it that much better than this one? Who knows? Um, all right, and you would have used O of k space, or and another way to, yeah, I think you would have used O of k space because if you were to generate random numbers each time, hopefully you'd be using your memory efficiently. In which case, you would throw out the ones that you're not using, um, and only have k numbers that you're storing at any given time. All right. So those are two acceptable algorithms, but we are going to focus on this one, which is the heart of reservoir sampling, and why that this is indeed correct. All right, and to do that, you can skip to the rigorous mathematical proofs, or you could stick around to where I sort of talk about how you would build an intuition for what that probability is and why that's correct. Okay, so one thing to do is forget about k elements. How do I even pick one element fairly? What if I have n is known, n is not unknown prior to start? How do I even pick one element fairly? Well, if I had two apples, you know, I have to give every apple, a half shot. If I have three apples, I have to give, sort of a 1/3 shot. So suppose for every element that I added, that I chose to replace the existing probability with probability 1 over n, which is to say, okay, I take the first apple, I have it in my hand. The second one comes and I multiply it by a half because it's the second item. And so with 1/2 probability, I replace the first apple. Now the third apple comes along, and I go, oh, gee, I don't know. Uh, and now you replace that with a 1/3 probability. And so this is the procedure that you would have chosen. And intuitively, you realize if you are to give each element a fair shot of being chosen, as n increases, the probability that an element is chosen needs to decrease as well. And so perhaps that's a key insight that was missing if you said, why can't I just flip a coin and pick a random index? So if you so if coming back to the problem, if you were to replace an element, what is using this procedure? What is the probability that the first apple is selected? Well, the probability that the first apple is in the solution would be 1 times the probability that it was 1 minus the probability that it would be replaced the second time, times 1 minus 1/3 the probability that it would be replaced the third time, and so on and so forth all the way to 1 over n. And it turns out that you have this wonderful little product in which the denominators and the numerators all cancel out to the point where the probability that the first apple is in the solution is 1 over n, which shows that indeed this procedure is fair, and that if I were to, the probability that, for example, the second apple or the third or the ith apple in a stream of n elements would be selected would still be 1 over n, where n is the place where you stop this procedure. So that's how you select one element. And so that should give you an idea of what's coming if you were to select k elements. So in order to prove this, you need to prove roughly three things, which maybe the first two can be collapsed. But you need to prove that the probability that one element I is selected is equal to the probability element j is selected for every element in n. In other words, no matter where I go, each I and j have an equal probability of being chosen. And another way of saying this would be if I stop the algorithm at any point at arbitrary point n, that the probability any element of being inside the solution is the same, which is k over n. So every element, the probability that every element has a chance of being in the distribution is k over n, or sorry, the reservoir. And the third one is that when you think of all the possible ways for n to select k elements, well, that is represented by nk, n choose k. So there are n choose k permutations of subsets, so the probability that I have any particular subset should be 1 over n choose k. So these are the three things that you could attempt to prove. All right, let's look at the first one. So this is saying for all I and j in a member of n, the probability that element I is in the solution should equal the probability that element j is in the solution. And we're going to do this by induction. And so the key here is what happens to the probability that I is in the reservoir at the I plus 1th step. So we're going to show that this is the probability that I is in the reservoir, and let's show that it's the same as the I plus 1th step. So the probability that element I is in the reservoir is not only the probability that it's chosen, which was k over I, but also multiplied by the probability that it is not replaced. Okay, and the probability that element I plus 1 is in the reservoir is k over I plus 1, because that's our procedure. And so the probability that element I selected is k over I, because that's how we selected. And the probability that it's not replaced, or that it is replaced, is k over I plus 1 times 1 over k, because that varies one specific spot in the reservoir is where it would have landed. So this cancels out and eventually turns into k over I plus 1, which is equal to the probability that element I plus 1 was selected. So we have shown that the probability that element I is in the reservoir is also the same as the probability that element I plus 1 is in the reservoir. Now, if you're satisfied by this, great. Our job is done. Or you could stick around for the other proofs, which is, how do you prove that if stopping the algorithm at any arbitrary point n, that the probability of any element being inside the solution is k over n? All right, so this is very similar to this is very similar to the solution above. And so the probability that I is in the solution is equal to k over I times the probability that it wasn't replaced. And so each time it has 1 over I plus 1 chance of being replaced, because we're replacing, or the probability that it lands in the reservoir is k over I, but the probability that it lands in that one specific point is 1 over I plus 1 each time. And so you have this series, and that series boils down to k over n when you expand this out. All right. Okay, that is the second proof. And this is the one that I had the least intuition for, but which is, how do you know that it is indeed the case that, okay, you've shown that if you, the probability that any element exists in the reservoir is k over n. Is that the same thing as saying that each subset k of over n elements has an equal chance of being chosen? In other words, is it the case that the probability that I see this subset is 1 over n choose k? How is that the case? This is like a whole bunch of factorials and whatnot, and this is a fraction. So why is that the same? I'm going to give it a shot based off the things that I've seen on the internet. And so the way that they're thinking about it is that it is the probability that, let's assume that this is the case. I assume that this is another induction proof. Let's assume that the probability that I'm choose any subset is this. There are only two cases that I need to consider, which is that the nth element of that is already in that subset, or that it needs to be added on the nth try. So the probability that that last element is already in that subset is n minus 1 choose k over 1 times the probability that it doesn't get replaced. In other words, that at the nth draw, that it doesn't add anything to the reservoir. which is 1 minus k over n. And so if you sort that out, it magically resolves to n choose k, or the inverse of n choose k. So the other half is a lot trickier, which I'm going to be honest, I don't truly fully understand this, is that there are n minus k, k-size subsets that don't contain the nth element that we are searching for. Thus, the probability that that last element is not in that subset of size k that we have is n minus k over the inverse of n minus 1 choose k. So if we want to replace the last element here. So this is the probability that I have one of those subsets. And then I want to replace exactly that last element. So the probability that that happens is k over n times 1 over k, as in that one exact cell, right, or position in the array. And so if you multiply this out, sure enough, the probability that that nth element gets added is also n choose k, or the inverse of n choose k. All right, that is all, folks. I hope that this was helpful, and I hope you ace your interviews. Jeeves out.